Chapter 11 Network Address Translation for IPv4 NAT. Public IPv4 addresses are not enough to assign a unique address to every device connected to the Internet. Commonly, the networks are implemented using private IPv4 addresses that allow devices to communicate locally. However, these addresses do not identify any single organization, so they cannot be routed over the Internet. So, how can we allow a device with a private IPv4 address to access devices and resources outside of the local network? By translating the private address to a public address. NAT provides this translation. NAT-enabled routers can be configured with several valid public IPv4 addresses, which are known as the NAT pool. When an internal device sends traffic out of the network, the router translates the internal IPv4 address to a public address from the NAT pool. To outside devices, all traffic that enters and exits the network seems to have a public IPv4 address from the pool. Commonly, a NAT router operates at the border of a stub network, which has only one connection to its neighboring network. When a device inside the stub network wants to communicate with an outside device, the packet is forwarded to the border router so it can perform the NAT translating process. In NAT terminology, the inside network is the set of networks that is subject to translation, while the outside refers to all other networks. In NAT, IPv4 addresses have different designations based on the network and the traffic. NAT terminology is applied from the perspective of the device with the translated address. An inside address is the address of the device which is being translated by NAT. An outside address is the address of the destination device. A local address is any address that appears on the inside portion of the network. A global address is any address that appears on the outside portion of the network. NAT includes four types of addresses. The inside local address is the address of the source as seen from inside the network. Inside global address is the address of source as seen from the outside network. Outside global address is the address of the destination as seen from the outside network. And finally, outside local address is the address of the destination as seen from the inside network. In this example, PC1 sends a packet addressed to the web server. The packet is forwarded from router 1 to router 2. When the packet gets to router 2, the router reads the source IPv4 address to determine if the packet matches the criteria specified for translation. Since it does match, it's translated from 192.168.10.10, which is the inside local address, to 209.165.200.226, which is the inside global address. Router 2 adds this mapping to the NAT table, and afterwards it sends a packet that has the translated source address toward the destination. The web server responds with a packet addressed to the inside global address of PC1. Router 2 gets the packet, checks the NAT table, and finds an entry for this mapping. Router 2 uses this information and translates the inside global address to the inside local address, and the packet is forwarded toward PC1. Now we are going to talk about types of NAT translation. Well, static NAT uses a one-to-one mapping of local and global addresses, and it's very useful for devices that must have an accessible address from the Internet, or even for devices that shouldn't be accessible by all users on the Internet when off-site, but only for authorized personnel. Dynamic NAT uses a pool of public addresses and assigns them on a first-come, first-served basis. So when an inside device requests access to an outside network, Dynamic NAT assigns an available public IPv4 address from the pool. And finally, port address translation. Well, PAT maps multiple private IPv4 addresses to a single or a few public IPv4 addresses. The ISP assigns one address to the router, but members of the household can access the Internet at the same time. With PAT, every private address is also tracked by a port number. When a device initiates a TCP IP session, it generates a TCP or UDP source port value. When the NAT router receives a packet from the client, it uses its source port number to identify the specific NAT translation. When a response comes back from the server, the source port number determines to which device the router forwards the packets. In this example, router 2 uses a port number to identify the device from which the packet was originated. For the source address, router 2 translates the inside local address to an inside global address with the port number added. The destination address can be referred as the outside global address. When the web server replies, the path is reversed. You can see in the last example that the client port numbers didn't change at the router, but there is a possibility that these port numbers might have already been used. When this happens, PAT assigns the first available port number. When there are no more available ports and there are several external addresses in the pool, PAT moves to the next address to try to allocate the original source port. This process will repeat until there won't be more available ports or external IP addresses. NAT provides several benefits. For example, it conserves the legally registered addressing scheme by allowing the privatization of intranets. It also increases the flexibility of connections to the public network. NAT provides consistency for internal network addressing scheme, and it provides network security, but it's important to remember that NAT doesn't replace firewalls. NAT has some drawbacks. Among them is the fact that network performance is degraded, particularly for real-time protocols. End-to-end addressing is lost. Using NAT also complicates tunneling protocols because it modifies values in the headers that interfere with the integrity checks done by these protocols. Services that require the initiation of TCP connections from the outside network can be disrupted. Unless the NAT router has been configured to support such protocols, incoming packets cannot reach their destination.
A static NAT is one-to-one mapping between an inside address and an outside address. A static NAT allows external devices to initiate connections to internal devices using the statically assigned public address. The static NAT translates the public IPv4 address to the private IPv4 address. There are two basic tasks when configuring static NAT translations. The first task is to create a mapping between the inside local address and the inside global addresses. After the mapping is configured, the interfaces participating in the translation are configured as inside or outside relative to NAT. The figure outlines the commands needed to configure a static NAT. Using the previous configuration, the figure illustrates the static NAT translation process between the client and the web server. The client wants to open a connection to the web server. The client sends a packet to the web server using the public IPv4 destination address. This is the inside global address of the web server. The first packet router 2 receives from the client on its NAT outside interface causes router 2 check its NAT table. The destination IPv4 address is located in the NAT table and is translated. Router 2 replaces the inside global address with the inside local address, then forwards the packet towards the web server. The web server receives the packet and responds to the client using the inside local address. Router 2 receives the packet from the web server on its NAT inside interface, with source address of the inside local address of the web server. Router 2 checks the NAT table for a translation for the inside local address. The address is found in the NAT table. Router 2 translates the source address to the inside global address and forwards the packet out of serial interface toward the client. The client receives the packet and continues the conversation. Here are some commands to verify a static NAT. The show IP NAT translations command shows active NAT translations. Static translations, unlike dynamic translations, are always in the NAT table. Show IP NAT statistics. Displays information about the total number of active translations, NAT configuration parameters, the number of addresses in the pool, and the number of addresses that had been allocated. The clear IP NAT statistics command to clear statistics from any past translations. The show IP NAT statistics command to verify that the statistic NAT translation is taking place on the router. Dynamic NAT allows automatic mapping of inside local addresses to inside global addresses. These inside global addresses are typically public IPv4 addresses. Dynamic NAT uses a group or pool of public IPv4 addresses for translation. The difference between static and dynamic NAT is that static NAT creates a permanent mapping to a single address, while dynamic NAT uses a pool of addresses. The pool of public IPv4 addresses is available to any device on the inside network on a first-come, first-served basis. With this type of translation, there must be enough addresses in the pool to accommodate all the inside devices needing access to the outside network at the same time. If all of the devices in the pool have been used, a device must wait for an available address before it can access the outside network. Here we have the steps to configure dynamic NAT. First, define the pool of addresses that will be used for translation using the IPNAT pool command. Second, configure a standard ACL to identify only those addresses that are to be translated. Third, with the third command, we bind the ACL to the pool. In step 4 and 5, we identify which interfaces are inside or outside in relation to NAT. Using the previous configuration, the figures illustrate the dynamic NAT translation process between two clients and the web server. In this figure, the traffic flow from inside to outside. PC1 and PC2 send packets requesting a connection to the server at the public IPv4 address. Router 2 receives the first packet from PC1, because this packet was received on an interface configured as an inside NAT interface. Router 2 checks the NAT configuration to determine if the packet should be translated. The ACL permits this packet, so Router 2 will translate the packet and check its NAT table. Because there is no translation entry for this IP address, Router 2 determines that the source address must be translated dynamically. Router 2 selects an available global address from the dynamic address pool and creates a translation entry. The original source IPv4 address is the inside local address and the translated address is the inside global address in the NAT table. For the second host, repeats the procedure, selects the next available global address from the dynamic address pool and creates a second translation entry. Router 2 replaces the inside local source address of PC1 with the translated inside global address and forwards the packet. The same process occurs for the packet from PC2 using the translated address for PC2. In this figure, the traffic flows from outside to inside. The server receives the packet from PC1 and responds using its IPv4 destination address. When the server receives the second packet, it responds to PC2 using its destination address. When Router 2 receives the packet with the destination IPv4 address of 209.165.200.266, it performs a NAT table lookup using the mapping from the table. Router 2 translates the address back to the inside local address and forwards the packet toward PC1, and the same happens for PC2. PC1 and PC2 receive the packets and continue the conversation. Here are some commands to verify dynamic NAT. The show IP NAT translation command displays all static translations that have been configured and any dynamic translation that have been created by traffic. Adding the verbose keyword displays additional information about each translation. The command clear IP NAT translation to clear all translations from the table. Another useful command is show IP NAT statistics, which displays information about the total number of active translations.
Now we're going to talk about path
Well, PAT, also called NAT overload, allows a single public IPv4 address to be used for hundreds, even thousands of internal private IPv4 addresses. When this type of translation is configured, the router maintains enough information from higher level protocols, TCP or UDP port numbers. There are two ways to configure PAT, depending on how the ISP allocates public IPv4 addresses. The first one is configuring PAT for a pool of public IP addresses. If a site has been issued more than one public IPv4 address, these addresses can be part of a pool that is used by PAT. This is similar to dynamic NAT, except that there are not enough public addresses for one-to-one mapping of inside to outside addresses. The small pool of addresses is shared among a larger number of devices. The image shows the steps to configure PAT to use a pool of addresses. The second one is configuring PAT for a single public IPv4 address. The image shows the topology of a PAT implementation for a single public IPv4 address translation. The traffic flows will be identified by port numbers in the NAT table, because the overload keyword was used. These are PAT configuration steps. Analyzing PAT. The process of NAT overload is the same whether a pool of addresses is used or a single address is used. PC to server process. Well, in this example, both PC1 and PC2 are sending packets to server 1 and server 2. The packet from PC1 reaches router 2 first. Using PAT, router 2 modifies the source IPv4 address to 209.165.200.225. There are no other devices in the NAT table using port 1444, so PAT maintains the same port number. Well, next the packet from PC2 arrives at router 2. PAT is configured to use a single inside global IPv4 address for all translations. Similar to the translation process for PC1, PAT changes PC's to source IPv4 address to the inside global address. Although PC1 and PC2 are using the same translated address, the inside global address of 209.165.200.225 and the same source port of 1444, the modified port number for PC2 makes each entry in the NAT table unique. Now server to PC process. As shown in the image, in a typical client-server exchange, server 1 and server 2 respond to the request received from PC1 and PC2. The servers use the source port from the received packet as a destination port and the source address as a destination address for the return traffic. As the packets arrive, router 2 locates the unique entry in its NAT table using the destination address and the destination port of each packet. When the packet from server 2 arrives, router 2 performs a similar translation. The destination IPv4 address of 209.165.200.225 is located, again, with multiple entries. However, using the destination port of 1445, router 2 is able to unlikely identify the translation entry. The destination IPv4 address is changed to 192.168.10.11. In this case, the destination port must also be modified back to its original value of 1444, which is stored in the NAT table, and the packet is then forwarded to our PC2. Verifying PAT. The same commands used to verify static and dynamic NAT are used to verify PAT, as shown in image. Port forwarding. Port forwarding, sometimes referred to as tunneling, is the act of forwarding a network port from one network node to another. This technique allows an external user to reach a port on a private IPv4 address from the outside through a NAT-enabled router. Configuring port forwarding with iOS.
Implementing port forwarding with iOS commands is similar to the commands used to configure a static NAT. Port forwarding is essentially a static NAT translation with a specified TCP or UDP port number. Verifying path. The same commands used to verify a static and dynamic NAT are used to verify path, as shown in image. The show IP NAT translations command displays the translations from two different hosts to different web servers. And the show IP NAT statistics command verifies that NAT pool 2 has allocated a single address for both translations. Port forwarding. Port forwarding, sometimes referred to as tunneling, is the act of forwarding a network port from one network node to another. This technique allows an external user to reach a port on a private IPv4 address from the outside through a NAT-enabled router. One important characteristic is that port forwarding can be configured to identify specific ports that can be forwarded to inside hosts. Port forwarding allows users on the Internet to access internal servers by using the one port address of the router and the matched external port number. Similar to static NAT, the show IP NAT translations command can be used to verify the port forwarding. IPv6 was developed with the intention of making NAT for IPv4 with its translation between public and private IPv4 addresses unnecessary. However, IPv6 does implement a form of NAT. IPv6 includes both its own IPv6 private address space and NAT, which are implemented differently than they are for IPv4. IPv6 unique local addresses are similar to RFC 1918 private addresses in IPv4, but there are significant differences as well. The intent of unique local address is to provide IPv6 address space for communications within a local site. Unique local addresses are also known as local IPv6 addresses and have some characteristics including: first, allows sites to be combined or privately interconnect, without creating any address conflicts or requiring renumbering of interfaces that use these prefixes. Second, independent of any ISP, and can be used for communications within a site without having any internet connectivity. And not routable across the internet. However, if accidentally leaked by routing or DNS, there is not conflict with other addresses. NAT for IPv6 is used in a much different context than NAT for IPv4. The varieties of NAT for IPv6 are used to transparently provide access between IPv6 only and IPv4 only networks. NAT for IPv6 should not be used as a long-term strategy, but as a temporary mechanism to assist in the migration from IPv4 to IPv6.
When there are IPv4 connectivity problems in a NAT environment, it is often difficult to determine the cause of the problem. In order to verify that NAT is operating as expected, we can follow the next steps. Step 1. Based on the configuration, define what NAT is supposed to achieve. Step 2. Use the show IP translations command to verify that exist correct translations in the translations table. Step 3. You can use the clear and debug commands to verify that NAT is operating as expected. You have to verify that dynamic entries are recreated after they are cleared. Step 4. Review in detail what is happening to the packet and verify that routers have the correct routing table to move the packet. We can use the debug IP NAT command to verify the operation of the NAT feature by displaying information about every packet that is translated by the router. The debug IP NAT detailed command generates a description of each packet considered for translation. With this command, we can get information about errors or exception conditions.